Density of states. The number of states available for the electrons to occupy in allowed state is called density of states. Or else, number of allowed states per unit volume can be called as density of states. Let us consider an atom. Atom is spherical in shape, and let us take one octant of the atom. So we have drawn that one octant of the atom separately here. So this in the octant, let us consider a direction, a quantum space n, which is designated with nx, ny, and nz. And let us further discuss that here we have taken two quantum spaces with n radius, first one with blue color, and n plus dn is the second one with the radius of n plus dn. So the energy of the first sphere is E and the second sphere is E plus dE, right? So between this E and E plus dE, that we have so many allowed energy states, right? So now the volume of the sphere given by 4 by 3 pi n cube. As we are considering only the one octant, the number of available energy states energy states in one octant of sphere of radius n is equal to 4 1 by 8 into 4 by 3 pi n cube. Now the number of available states energy states in one octant of sphere of radius n plus dn is equivalent to 1 by 8 into 4 by 3 pi n plus dn whole cube. Now we have number of available energy states in one octant of sphere of radius n 1 by 8 4 by 3 pi n cube with energy E, and another octant 1 by 8 4 by 3 pi 10 plus n whole cube of energy E plus dE, right? So now the number of energy states, let us try to find out. So let us try to find out the number of energy states having energy having energy between E and E plus DE. So how many number of energy states are there? That we are going to represent with N of E DE, which is equivalent to 1 by 8, 4 by 3 pi n plus dn whole cube minus 1 by 8, 4 by 3 pi n cube. So further simplification, n of E dE is equal to 1 by 8, 4 by 3 pi, also will take common. So what is left out in the parenthesis is n plus dn cube minus n cube. So expanding n plus dn cube like a plus b whole cube, n of E dE is equal to, so here 4 ones are 4 twos are, so I can write this as pi by 6 n cube plus dn cube plus 3 n square dn plus 3 n dn square minus n cube. So what is happening here? Minus n cube plus n cube cancel, ignoring dn square and dn cube terms, as dn is small. So what happens? N of E dE is equal to pi by 6 3 n square dn. So 3 1 ja, 3 2 ja, it is going to be 5 by 2 into n square dn. Further, the same can be written as 5 by 2 into n into n dn. Now let us try to find out what is the value of n. Already according to quantum theory, we know that E is equal to n square h square by 8 m l square. So writing for n square, so n square is equal to, n square is equal to 8 m l square by 8 ml square by h square into E. So what we are looking for is n and ndn. So n is equal to 8 m l square by h square whole power 1 by 2 into e power 1 by 2. So similarly n dn is equal to how much? 4 m l square by h square dE. So substituting the value of n and n dn in this expression, so what we are going to get is n of E dE is equal to pi by 2 into n value. What is n value? 8 m l square by h square to the power of 1 by 2 e to the power of 1 by 2, and ndn value is 4 m l square by h square into dE. So further, uh, dividing and multiplying this expression with 2, so what happens? So in this case, it becomes equivalent to n of E dE is equal to pi by 2 8 m l square by h square whole power 1 by 2. So at this 2 we will multiply with here, so it becomes 5 by 4 So what is left out here is 8 m 2 4 is 8. So 8 ml square by h square into e to the power of 1 by 2 d. So here you see it is to the power of 1 by 2, and here we have 1. So now n of e d becomes equals to pi by 4 8 m l square by h square whole power 3 by 2 e power 1 by 2 d, right? So that is NEDE. But according to Pauli's exclusion principle, according to Pauli's exclusion principle, what we have two electrons in each momentum space. So n of E dE is equal to 2 into pi by 4 8 m l square by h square whole power 3 by 2 e power 1 by 2 dE, right? So now n of E dE can be written as, so what we have here, 2 1 ja 2 2 ja 4, so pi by 2 into 8 m L square by h square whole power 3 by 2 e power 1 by 2 dE. So further n of E dE is equal to pi by you see here h square whole power 3 by 2. So we can write it as h cube. And similarly 8, instead of 8 we can write it as 2 into 2 square. 2 square whole power 3 by 2. How much? 2 cube. 2 cube value is 8. So here we will get 8. 8 divided by 2. So 4. 4 5 by h cube into, what is the left out thing here? 2m to the power of 3 by 2 into L cube e power 1 by 2 dE. So these are the number of available states between E and E plus dE. But what we are looking for is density of states. What is the density of states? Definition says that the density of states ZEDE is equivalent to number of available states per unit value. So here Z of E dE is equal to, so n of E dE 4 by h cube 2m to the power of 3 by 2 L cube e power 1 by 2 dE by volume L cube. L cube cancel. So finally, what is the expression for density of state is ZE dE is equal to 4 pi by h cube 2m to the power of 3 by 2 e power 1 by 2 dE. So this is the expression what we are looking for.